Hello, my name is Nasniewski, and we're going through this monoidal category theory book. We're learning a lot about category theory. Okay, so we're up to chapter 2, categories. We're up to section 2.2, which is about basic properties. So let's go through it. Last video, we went through tens and tens of different categories, examples of categories. And now that we have something we can talk about, so now we want to talk about different properties of categories. So we're going to talk about what does it mean for a diagram to commute. We're going to talk about what are special types of morphisms within a category, and then we're going to talk about special types of objects within a category. So lots of different things within a category. Okay, so first idea is, what does it mean for a diagram to commute? So I drew some of these diagrams already, okay? And basically what it says is, for a diagram to commute means if you take any place, okay, any object, and take any other object, okay, and if there are two paths through the arrows, with arrows, two paths for them, so for example, there's two paths from here to here, well, it commutes means that if you compose this map, you get this map, okay? Same thing here. Start here and here, there are two different paths. If you compose this map, you get the same thing. It's the same map as that map. So that's what it means for a diagram to commute. This is a little bit more abstract, okay? And it's as follows. F, first do G and then F, is the same thing as H and then F, okay? So it's, from here till here, you get the same thing. Not G and H are not necessarily equal, but this is true. Now, we saw this before when we introduced the definition of category. We needed associativity, which means if you have three different maps together, if you have three different maps, then you can compose them in different ways. And what we want is to be commutative, which means that this map is the same as this map. Okay, so that's what associativity of composition means. We didn't write up this example, but basically it's the same. This is about units. You have the identity from A to A. You have a map from A to B. The compose of them, you want a map from here to here. There's two different ones. Here's one, here's the other. Okay, and you want them to be the same. Same thing here, F composed with identity of B. You want these two different ways of going from here to here. You want them to be the same. Okay, so lots of examples of such things, okay, and totally understandable, and again, we're going to use it all the time. Okay, great. Okay, so now that we write this, with this idea of commutative diagrams, we can write a lot of requirements very, 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 very quickly and things like that. So now I want to talk about special types of morphisms within a category, okay? And so we have as follows. Okay, now we're going to talk about special types of morphisms. Okay, so imagine the following. Okay, and we're going to call those G and H and F. Okay, so here's the following. F is called a monomorphism. Okay, mono from one, morphism, homomorphism, monomorphism, or sometimes it's mostly shortened to mono or monic. Okay. Okay, it's a monomorphism if the following is true. If first F and then G, if you first do G and then F equals to H and then, F and then H. In other words, if this composed with this is equal to this composed with this, that implies, this is when F is a monomorphism, that G is equal to H. Okay? Okay? This has another name. It's called left cancelable, or something like that. Cancelable. Okay? Namely, notice F compose G, F compose H. If it's left cancelable or monic, then you can cancel the F and you just get G is equal to H. Okay, now let's look at it from this point in the category of set, because that's where we get our intuition. Okay, imagine C is the one object set, okay, and G and H pull out one element of S. Each one of them pulls out one element of S. Okay, and so we ask the following question. What does it mean for a function from S to T to be a monomorphism in the category of sets? So let's do this. So basically, G picks out an element of S. H picks out an element of S. And so you have G of star. Okay, and then you do F of it. Okay, and if we're assuming this to happen, G composed F is equal to H composed F, so then you have F of H of star. So basically as follows: G of star is an element, H of star is an element. If F of that element, okay, is equal to F of the other element, the only way that can possibly be is if G of star equals H of star. Okay, and in sets, this is called a one-to-one function. Let's just remember. A one-to-one function is where no two things come to one thing. No two S's come to one element of T. Or another way of saying it is, if two elements come to one element, then it must be that those two elements are the same. And that's exactly what this says. If two elements, this and this, come to one element, they're equal, then it must be that G star, the element that G picked out, is the same as the element that H picked out. So in the category of sets, a monomorphism is a one-to-one function. Okay, but we like these definitions because when we were talking about sets, in order to tell you what a one-to-one function is, we had to talk about elements of the sets. Okay, so we say two elements here going to one element here, but here we're just talking about maps and compositions. That's it. And so that's more categorical. Okay? Okay, so what we're going to have is, sometimes we're going to have categories, and the categories are going to have certain morphisms, and the morphisms are going to be monomorphisms. And we're going to go through lots of examples and showing which categories have monomorphism, what are monomorphisms, and things like that. The intuition that you should think of is a monomorphism is some type of inclusion or some type of one-to-one function, and we have to worry about when it is and when it's not. Okay, in contrast, we have another type of morphism called an epimorphism. Okay, sometimes it's shortened to just an epi, okay, and it's also called a right cancelable, or something like that. Okay, and it goes as follows. You have a map from F from A to B, and you have two maps like this from B to C. We'll call this G and H, and we have the following requirement. If F compose G is equal to F compose H, so now we do F first, and then we get these two things. Well, if it's an epimorphism, if it's right cancelable, then, okay, you ready? G equals H. So F has the following property. Any two maps coming out of its codomain, if the composition is equal, then it must be that the composition, then the two maps must be exactly one map. Okay? Okay, let's just say it in, I don't want to go through the details. In set, epi means onto. Okay? And the idea is as follows. Basically, in set, so you have F from S to T, if it's going to be onto, then it's going to cover every element. And so when it does this furthermore, then it must be that it covered every element, and it got that. Okay, so you look in the function in the book for exact definitions, so exact working out all the details. Main thing, why is it called right cancelable? Because the f is on the right, and we cancel it, and we get g is equal to h. Okay, so great. So now we have two types of morphisms. We got monomorphisms, we got epimorphisms. Okay, great. And now we have a third type called as follows. Okay, F is an isomorphism. Okay, if there's another element, there's another map G such that F compose G is equal to the identity, start at A, go there, the identity in A, and F compose G, so start with G, then do F, okay, and that's equal to the identity on B. That's what an isomorphism is. Again, okay, we'll talk about its relationship with epi and mono in a second, but the main point is this is a category theoretic definition. It's only talking about morphisms and compositions of morphisms. So that's very nice. In such a case, we write G as F minus 1. We can write F as G minus 1 also. Okay? And there's a lot of nice properties about isomorphisms. Okay, if two elements have such an isomorphism, if an object A and an object B have an isomorphism in between them, they're called the objects are called isomorphic. Okay. Okay, great. Okay, and just a quick theorem, which is obvious. Okay, so let me just say another thing, namely, the identity morphism is an isomorphism. The inverse is the identity morphism. Okay, and composition of isomorphisms is an isomorphism. These are exercises, but it takes 5 minutes to do. But I want to do one theorem that shows the relationship between these things. So theorem, okay, F is iso. That implies F is mono and epi. An isomorphism is both mono and epi. It doesn't. Okay, and the idea is as follows. You use the inverse as follows. So let's just do it. If F composed G is equal to F composed H, okay, then use the inverse of F on both sides of the equation. So let's go through this. Here's a map. Here's a map. We can compose with F inverse, and we get F compose G. Okay, we can compose it on this side too. We get F inverse composed with F composed with H. Okay, now we have a special name for F composed F inverse. We call that the identity. Okay, so we call this the identity. Okay, and so what you get is G composed with the identity is equal to H composed with the identity. This means G is equal to H. Okay, so that shows that F is either epi or mono. So this shows that it's right cancelable. Okay, great. Okay, good. Let's go back, talk about isomorphisms, because we like isomorphisms. They make things more interesting. So we want to talk about two types of categories. One is called a groupoid. That's an algebraic structure, but it's a little bit more complicated than anything else we talked about. And basically, this is a category where all the morphisms are isomorphisms. All the morphisms are isos. Okay, so that's called a groupoid. Okay, so you have a bunch of objects and you have isomorphisms, only isomorphisms between them. These show up everywhere. Okay, and we're going to talk about them. They are a way of describing a certain type of symmetry. Fine. Now, another type of group, okay, an example of a groupoid, a one object groupoid, let's just show you what that looks like. That's one object over here, and lots of morphisms from that object to other objects, okay? But every one of these objects are isomorphism. The way you write isomorphism is you put a little twiddle on it. So they're isomorphisms, okay? So you can undo every one of those objects. Such a thing is called, you guessed it, a group. A one-object groupoid is a group, okay? Now we saw group twice. We saw it in section 1.4, we gave a formal definition. Then we saw it in section 1 and 2.1, where we gave it again, okay, as an example of an algebraic theory. I'm sorry, of an algebraic structure. That's very nice. But now we have another way of looking at it. It's a one-object category where all the morphisms are isomorphisms. We saw something else as a one-object category. What was that? Monoids. So every single monoid is a one-object category. Now, special types of monoids where every single morphisms have an inverse is called a group. So let's just go through that. A monoid with invertible elements is a group. Okay, so we're seeing these structures in different ways. Okay, you can think of them as a set with different operations. Okay, or you can think of them as a one-object category. You can think of this as a one-object category. A group is a one-object category with all the morphisms are invertible, and a monoid is just a one-object category. It doesn't necessarily have to be all invertible. Okay, great. Okay, so let's recap. We saw special types of morphisms. Some morphisms are called monomorphisms. Some morphisms are called epimorphisms. Some morphisms are called isomorphisms. That's very nice. Okay, now I want to talk about special types of objects. Okay. Basically as follows. We have an initial object. Okay. An initial object in a category is some object I such that for any other object A, B, any other objects, there is a unique, we write unique like that, a unique morphism from here to there. Okay? So any morphism, any other object in the category, there's a unique morphism from I to this. When this is true, I is called an initial object. Great. We always, just like you saw epimorphism and monomorphism is just turning the arrows around, so too we can turn the arrows around about an initial object, and we can talk about a terminal object. Okay, what's a terminal object? Well, it's an object in the category, and for any other morphism, for any other object in the category, there's a unique map like this. Again, categories need not have initial objects or terminal objects, but if they do, they have this. Okay? There's a third type of special object called a zero object. Okay? A zero object is an object, we'll call it Z, that is both an initial object and a terminal object, which means for any object A, there's a unique morphism there. For any object B, there's a unique morphism there. So those are called zero objects. Okay, let's look at some examples. Well, first examples we're going to look at is in set, because that's where we get our intuition. The initial object is the empty set. We said this before, for every single set S, there is a unique morphism from the empty set to S. Okay, what about a terminal object? Well, any one object category, okay, has the following property. There's a unique morphism from there to there. Okay? Now, the category of set does not have a zero object because the empty set is not the same as a one object category. But there's something more important here. Not only is this a one object, this one object category is a unique, this is a terminal object, but there's another terminal object too. Okay? For any object, one object category, there's a unique map like that. Okay? And here's another one. In fact, in the category of sets, there are a whole class of terminal objects. Any one object category is a terminal object. Okay? In set, there is no zero object. The empty set is not the same as a one object category, therefore there is none. Okay? Let's talk about something else. In prop, this is propositions, this is in logic, the initial object looks like this. It's kind of false, and the idea is any proposition P, false implies any proposition P. Now, initial objects are easy to find in props because there is only one object. There's only one morphism between any two objects anyway, so if you have it, it's there. Okay? Next, in prop, a terminal object is usually called T for true. Okay? P implies the truth, and usually there's no zero object. Okay? In a category which is a pre-order or a partial order, okay, the zero is less than we usually write zero as the initial object. So there's zero is less than any element, okay, and any element is less than. We usually write the top of that as 1. Okay, so when we need this, we'll see it. So again, these are 3 special types of objects in the category. Great. Okay, now let's talk about something important. There is only one initial object in the category of sets, but there are many, many terminal objects in the category of sets. Okay, and I want to know what the relationship is. Well, it turns out between any two terminal objects, there's exactly one isomorphism in between them. So I want to make that as a theorem, and I want to actually go through this extremely slowly and carefully. And the reason why I want to go through it so closely and carefully is because we're going to see many, 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 many theorems of this type when we talk about special properties of objects and categories. Okay, so let's write it as a theorem, and we're going to slowly prove it, and you'll see, this is the last time I'm going to prove it, all the proofs are basically similar type. To this, all the proofs of this type of theorem is basically the same. So if we get this, we get it. There is a unique isomorphism between any two initial objects. Okay, so this is a new type of idea here. Okay, so a lot of times we say something is unique. Okay, so the natural numbers is unique, 0, 1, 2, 3, 4. So that's unique. You can't change that. Okay, something is unique. And then sometimes we have some things where they're not unique, but there's an isomorphism in between them. Let's just look at 3-element sets, A, B, and C. Okay, here's another 3-element set, X, comma, Y, comma, Z. Okay, this has an isomorphism in between them. But you know what? It has many isomorphisms in between them. In fact, it has 6 isomorphisms in between them. Okay, there's 6 different isomorphisms in between them. Okay, but there's something a little bit more special if you have, so this has 6 isomorphisms in between them. If you have some object and you have a unique isomorphism in between them, okay? So there's only one. Okay, great. So I want to show you how you prove this. So there's a unique isomorphism between any two initial objects. The same theorem goes with terminal objects too. We saw that in the category of sets. There are many different terminal objects, And so you have, but there's a unique isomorphism in between them. Now, in the category of set, this doesn't even make sense. It's not interesting because there's only one initial object, and that's the empty set. Okay, but now I want to talk about an arbitrary category and many different types of categories, and we're going to see many different types of categories, and we're going to ask the same question. Does it have an initial object? Does it have a terminal object, over and over? Okay, so I'm not talking about any category. We're in the category A. I have no idea what A is, but let's go through this. What we have is as follows. Let's say there are two initial objects, I and I prime. Okay, great. Now, from the fact that this is initial and this is an object in the category, means that there's a morphism from here to here. A unique morphism from here to here. Okay, that's what it means to be an initial object, for I to be an initial object. Okay, great. Now, I'm sorry, I shouldn't have drawn that. Hold on. Now let's look at I prime. I prime is also an initial object, which means that if there's another object, there's a unique morphism there. Okay, great. I want to just do that one more time. If there's another object, I, then there's a unique morphism, and I told you what the unique morphism is over here. So we have F. Okay, great. Now, what about a morphism from I? I is an initial object. I is an object of the category. Well, there's a unique morphism from here to here. What should we call that unique morphism? Oh, well, I know every category has such a thing, and so I'm going to call this identity on I. Okay, so stop. What does this mean? That F compose G is, because we know that there's only one morphism from here, so here's two seemingly different. One is identity of here, and one is this composed with this. But we know there's only one morphism from I to I. Conclusion, F compose G is equal to the identity on I. Hold on. What about that? Well, identity of I prime. Okay, and what this shows us is that G composed F is equal to identity also. Okay? Okay, now from these two things we have the following. F inverse is equal to G. G inverse is equal to F. Okay, so these are isomorphisms. We can write isomorphisms like this. Okay, so what did we just say? We said if there is more than one initial object, then there's isomorphisms in between them. Very nice. Now we have their isomorphisms. But what do we want to show? Not that there's isomorphisms. We know lots of times there are isomorphisms. But here we have something more special. There's a unique isomorphism, which means what? Okay, well, let's imagine that there's another isomorphism from here to here. We'll call that F prime. 1 second, that can't be. Why? Because what is the property of being an initial object? There is a unique morphism from here to here, which means there can't be two isomorphisms between them. Okay, there is a unique morphism, in particular, one is an isomorphism, the other is an isomorphism, so there's only unique morphism. So between any two objects, there is a unique isomorphism between them, so they're equal. Okay. Okay, so that's fascinating. Okay, and the reason why we like this is because we're going to talk about categories. We're always going to discuss the following difference. Okay, do we say the category A has a something something or the something something? Okay, when you say A, my hand has a finger on it. Okay, my right hand has the thumb. There's only one thumb. There are many fingers. There is a finger, there is the thumb. So you have this distinction. A is one of many, the is only one. Okay, so we're always going to discuss this. Okay, on page 63, there's a nice categorical idea, and we talk about this. Okay, there's a three-level hierarchy, which we like to talk about. So one is where something is unique. Okay. Where something is unique. We like things that are unique. Okay. Makes things very, very clear. Okay. The third level of the hierarchy is not that it's unique, but it's unique, and you're going to have to get the lingo straight, unique up to an isomorphism. Okay, let me just give you an example of something unique. The empty set in the category of sets is unique, or the initial object in the category of sets is unique. Okay, great. Okay, unique up to isomorphism means, well, the set of three elements is unique up to an isomorphism. Or something is unique up to isomorphism means what? If there are two of them, C and C prime, then there is an isomorphism in between them. But there could be 2 or 3 or 5 or 10 or infinite number of isomorphisms in between them. So that's what means unique up to an isomorphism. They could be more than one, but if there are more than one, there's an isomorphism in between. Could be many, okay? But we have an intermediate level of uniqueness, and what this is unique up to a, so it's very similar to this, unique isomorphism. Okay, and we're going to see that when we talk about different categories, sometimes we have this, sometimes we have this. Sometimes we would like this. This makes things a lot easier, but sometimes we don't have this, and so we have this. Unique up to a unique isomorphism. What does that mean? You could have one object, you could have another object that also has that property, but there's a unique isomorphism between them. Only one. Okay, and this is something we like. Okay, so we use the word the here. We don't use the word, we use the word a here. Okay, and we're going to use the word a here, but when we have this property, things are much more nicer. Okay, great. Now, let's go back and talk about the zero objects, the initial objects and the terminal objects and things like that. Okay, so let's talk about initial, terminal, zero. Okay, so let's talk about in sets, in topology, in manifolds, the initial objects are the empty set. The terminal objects are any one object category. Any one object set, topology, topological space, or manifold. Okay, they don't have a zero objects. Okay, what about a magma or a semigroup? Okay, these are things without an identity element. Anyways, there is an empty magma and an empty semigroup. That's the initial object in the category of magmas or semigroups. Okay, there is a terminal magma in the category of magmas. There's a terminal semigroup in the category. There's no zero. Okay, how about this? Monoids, groups. Rings are a little bit more complicated, so let's just talk about that. Monoids, commutative monoids, groups, commutative groups. Well, the initial object is just something that the one object monoid or the one object group is the initial object. you just take E to any other thing. There's only one place to move it to. Okay. Similarly, you have that. You have one morphism like that. Okay. And so the zero object in the category of monoids, the category of groups, the category of abelian monoids, the category of abelian groups is also this. It's the same thing. Okay. Rings. Okay, rings are interesting. They have pluses and minuses, and they have zeros and one. Well, anyways, the initial object in the category of rings is the integers. That's like the way to think of this is that's the smallest ring that you can possibly have, because it has a 0, it has a 1, it has plus, and it has multiplication. Okay. Okay, there's a terminal object if you have 0 is equal to 1. Don't want to get into that. Fields don't have an initial object and don't have a terminal object and don't have a 0 object. Okay, so that takes care of that. Okay, so fine. We just went through a few, what did we do this video? We just went through a few different special types of morphisms, special types of objects, and we got into this discussion of what uniqueness is all about. Okay, this is going to show up much later when we start talking about monoidal categories and coherence theory and higher category theory. Category theorists become obsessed with this notion of how unique something is, and they're trying to constantly show how unique something is and how, and for valid reasons to be obsessed with this. Okay, great. So this is section 2.2 where we talked about basic properties. Section 2.3 is where we talk about related categories, how given one category you can always get another category. Subcategories, opposite categories, quotient categories. We'll talk about that later on. And section 2.4 is going to be a deep dive into one particular category, namely the category of vector spaces. That's where linear algebra lives, and we're going to need that. So section 2.4 is a basic introduction to linear algebra. Take care.